Right, everyone. So we will continue with a new week and a new topic, and we are going to be looking at sea ice. And no beginning introduction to sea ice would be complete without the obligatory polar bear, really, would it? And in reality, that's just the top of the food chain that we see, and we're going to learn on Wednesday much more about what makes up the rest of this really unique ecosystem. That depending on our future emissions may or may not be around for too much longer. Can you hear me okay at the back today, or do I need to turn the microphone up? Great, thanks guys. Okay, so on this week to sea ice, we're done with permafrost. In discussion this week, you'll have a chance to have a go and look over that. So my first question for you is, which of these is sea ice, or are they both, or are neither of them sea ice? So what do you think? Which of those is of sea ice? Okay, any more opinions? Right, let's take a look and see what people think. So most people think both A and B. Some people think neither. In fact, there's just a mixture of all answers, really, isn't there? So what do we call B? An iceberg. And actually, an iceberg isn't sea ice. It formed on land, and the reason that we have icebergs is that glaciers, especially in high latitudes, it's so cold that glaciers flow to the oceans, and then bits of those glaciers break off and they float off in our oceans, and we get ginormous, really ginormous icebergs. But sea ice is something completely different. Sea ice is just when the sea freezes, when the sea gets cold enough that the top of it freezes. And so we don't get hundreds of meters high sort of sea ice. We get maybe a few meters at most. So what we traditionally see when we see ice floating in the ocean is B. Sea ice actually looks much more like A. Okay, so A is actually a picture of sea ice. It's very mature sea ice, so it's been around for a few years. But it has that sort of characteristic pattern of those ridges, and you can see where sort of parts of it have been pushed together. So we're going to learn much more today about sea ice. Okay, so what is it? It forms when that seawater gets so cold that the water freezes. So it is different, completely different from more or less anything else that we're going to look at. When we're going to spend the rest of the quarter after this week really thinking about land ice. Thinking about sort of snow forming glaciers, forming these much bigger glaciers and ice sheets. Okay, but sea ice is sort of unique in the sense that it is much more temporary in some ways. And so you can see that up in the Arctic, in March, that blue area is what is typically covered by sea ice today. And that sort of blue area in September shows the area covered typically by sea ice today. And of course, that September image is the one that we're most concerned about and really has the greatest potential to change in the next sort of few decades, or even the next sort of 1 or 2 decades. And then you can see at the same time we've got sort of large amounts of sea ice in September around Antarctica. Why do we have minimum sea ice in the Arctic at the same time as maximum sea ice in Antarctica? So moisture's something to do with it, but we're on the sea, so there's always certain amounts. Why do we get the most in the southern hemisphere when there's the least in the northern hemisphere? Yeah, absolutely, because our seasons are opposite, remember, okay? That's as complicated as it gets. So you can see that at the same time we have maximum sea ice in the Antarctic, we have minimum in the Arctic usually, and vice versa. Okay. So why is sea ice important? Why should you care? Why are we so concerned that it seems to be disappearing much more quickly than perhaps our computer models would suggest that it is? Well, first of all, it covers 7% of the world's oceans. And so if it is going to disappear, even if it is sort of seasonally, then is worth understanding what that is going to do to things like our energy balance and atmospheric exchanges of gases and energy. And so especially up in the polar regions, it limits that exchange of energy and heat when it's present. It also has that really high albedo. Nice, lovely white sea ice has an albedo of 80 to 90%. And so obviously we're concerned that if we're going to lose that, we're going to change Earth's albedo, and especially in the summer in those polar regions, we could absorb much more of the sun's radiation rather than reflecting it away. And so it's one of those things that we're initially affecting how much sea ice there is, but it's one of those positive feedback loops, whereas once we start affecting how much it is and melting it back, there's more exposed sea, which absorbs more energy, and so the temperature just gets higher and higher, and we get less and less sea ice. It's really important to the formation of something that you may not have heard of, which is thermohaline circulation. And this is really the process by which our whole oceans are circulating really, really slowly, maybe on 1,000 years or so. But our oceans do move. Everyone just thinks that they sit there like bathtubs with sort of full of water, but they're always moving. And the formation of sea ice and the melting of sea ice is really important for us being able to sink cold surface water really deep into our deep oceans and sort of move all of that ocean around. And so everyone's heard of the day after tomorrow, right? Yes. And so the idea is that every now and again, that sort of deep ocean circulation might switch off or might switch to a different state. And that won't happen in 3 days like the movie does, because Hollywood is Hollywood, but it has happened in the past. And we'll look a little about the evidence for that and why that happens, because it's a really interesting idea. It also just provides that wonderfully unique habitat that is special to so many of those creatures that we like to identify. And so in the southern hemisphere, we have our little penguins, and then up in the Arctic, we have our polar bears, and also things like seals, specific type of whales, but right down into the fundamental, the little plankton under the ice. Those are very specific to the Arctic, and as that sea ice disappears, then we're getting species invading in from the Pacific and the Atlantic. So really what is going to happen to our ecosystem there? And lastly, for all you economists and politicians in the room, most importantly for you guys, the Arctic Ocean has enormous stores of oil and natural gas, particularly natural gas. And so all of a sudden, no one was really particularly interested in the Arctic Ocean. But if we're going to have significant melt of sea ice, then all of a sudden, at least in the summer, we can get to it pretty cheaply and pretty easily. And so there's this sudden rush, like the equivalent of a gold rush, but to the Arctic Ocean, where things like that retreat of sea ice might open up new shipping routes across the top of the planet, rather than having to go through the Suez Canal and past that area where there's sort of increasing piracy, but also, of course, to exploit the wealth underneath the water. So lots of really interesting things, and we'll talk more about those last few in the next lectures. So just to remind you that we are a blue planet, we are a water planet, but really 97% of our water is actually in the oceans. Only 3% of it or so is fresh water, and the vast majority of that is locked away in ice, okay? So really today we're going to look at how that ice, a sort of layer on that 97% influences our Earth. Okay, so first of all, if we're going to talk about the oceans, it's worth checking that everyone knows where the oceans are and which ocean is which. So I'm always slightly horrified when people mix up the Pacific and the Atlantic. Okay, and so which ocean are you on? The Pacific. Good news. Okay, so this big giant one that you live at the edge of is the Pacific Ocean. Which is this one in the middle? The Atlantic, the one you fly across to get to Europe. What's this one over here? The Indian. And now we have two more. What are my other two? The Arctic, absolutely. And what's my fifth one? The Southern Ocean. Absolutely. Good work, guys. Okay. So I have my Pacific, my Atlantic, my Indian, and they're not so important for sea ice. But really, for now at least, the Arctic and the Southern Ocean are where sea ice is an important part to play in ecosystems and how it functions. Okay. So here are, again, some funny maps viewed from the top rather than at the side now, because those are the parts we care about. And you can see the Arctic on the left and the Antarctic on the right. And you can see that we have funny geography going on. What's the difference between the Arctic and the Antarctic in terms of its geography? Yeah, absolutely. They're mirror images, right? In the Arctic, we have an ocean surrounded by land. And in the Antarctic, we have land surrounded by ocean. Isn't that neat? No one seems that stunned, but it's really fun. And it does affect things like sea ice. Because when we have an enclosed ocean, then obviously that sea ice can develop right over the pole, whereas in the Southern Ocean, even though Antarctica is really cold and isolated, we get that sea ice forming around the edge. And when we come back, it's going to be my last iClicker question of the day. How does that affect how likely it is for sea ice to hang around for any length of time? Okay, so ocean surrounded by land, land surrounded by ocean. So let's talk a little bit more about ocean salinity, because really that's the fundamental difference between our oceans and our fresh water. So when we talk about salinity, what we really sort of talk about is the massive salt that is dissolved in our ocean water that makes it taste salty when you accidentally swallow it when you get drowned by a wave. Okay? And we express it in something called per mil, or parts per thousand. So I haven't accidentally messed up my percent sign. This is the sign that you use when you mean per thousand rather than per 100. So if you get 90% in your exam, you get 90 points out of 100. If you got 90 per mil, you would get 90 parts out of 1,000, which is entirely not so good, okay? And so that's what we use when we talk about seawater. So our typical range of salinities in the ocean today are somewhere between 33 and 37 per mil, or sometimes we call it PSU. For this class, we can call it equivalent, even though they're not. And so what that means is that in 1 kilogram of seawater, we have something like 33 to 37 grams of salt. So if you went down to the beach at Newport Beach and you collected a kilogram of seawater and you took it back to your apartment and you very patiently let it evaporate through time, at the end you'd have 33 or so, 34 grams of salt left over. And primarily, that's really mainly made up of sodium and chloride. Sodium chloride table salt. Those are really the main ions that are dissolved in seawater. And then there's a few other things in there like sulfate, magnesium, calcium, potassium bicarbonate, those sorts of things. Okay? That's what makes up our ocean salinity. And this is what our ocean salinity looks like on a map. If we were to look at a world map of just the surface salinity, you can see it here. So the redder the color, the higher salinity, and the bluer the color, the less the salinity is. So where are our high salinity areas? Whereabouts on the globe are they? Yeah.
Off the coast, or I guess like near. Wait, blue is high salinity or low salinity?
Blue is low salinity.
Okay, never mind.
Okay, we'll come back to you for low salinity. Where are high salinity areas?
In the Atlantic.
In the Atlantic, definitely, we've got some high salinity areas, but there's also a couple of pockets of higher salinity in the Pacific as well. You see they're located at specific latitudes, right? What sort of latitudes are they at? 20 to 30 or so? What latitude are we at? 30 something, yeah, absolutely. We're around 30 as well. What's our weather usually like outside? Hot and sunny, right? Okay. And so if we have that nice hot sunny weather extending at sort of 30 degrees Celsius, degrees north and south along our sort of oceans, what do you think might happen to create high salinity? Evaporation, absolutely. So if we have this nice sunny weather at sort of our particular latitudes in the world, then we're going to have more evaporation. And what happens during evaporation is we're taking that fresh water away and we leave that salt behind. So if we have lots of evaporation, that fresh water leaves and we get more salt left behind in the surface ocean. And so you can see that where we're warmer, And where we have more sunshine and less rainfall, we're going to have high amounts of salinity. So why do you think, or where are our low salinity areas?
Around the coast.
Around the coast, and where else?
You mean the Antarctic, I guess?
Yeah, absolutely. Near the poles, right?
Mm-hmm.
How much evaporation do you think we typically get in those areas? Not a lot, right? Because it's colder, okay? What else might be we getting off the coasts and off of Greenland and Antarctica? Sorry? Ice melting, absolutely. We have rivers going into the ocean. We have ice melting. We have fresh water from land running into the ocean and diluting it slightly. So just like evaporation takes away fresh water, if we can add fresh water back in, we're going to change our surface salinity. Okay, so remember that. Okay, and so we can change our surface salinity in a number of different ways. First of all, by evaporating, and we get rid of our sort of fresh water. Precipitation, so rainfall, snowfall, anything like that will dilute our seawater. Freshwater discharges from rivers or from ice melting will again dilute our seawater. And the last thing that can affect our ocean salinity is the formation and melting of our sea ice. Okay? And that's because when we form sea ice, that ice that freezes wants to be pure ice. It wants to just form this sort of fresh ice layer on the surface of the ocean, and that pushes out all the salt. The salt doesn't really like being in the salt structure, and so it gets pushed out below. Okay, and I've got a cool little video to show you of that a little bit later. Okay, so next let's look at temperature of our oceans. Where is it hottest in our oceans? Near the equator. Where is it coldest in our oceans? Near the poles. Okay, great. Really complicated stuff. So, my question for you is, what temperature does seawater freeze at? What temperature does seawater freeze at? Any more? Last few estimates? Okay, let's see how good everyone is at this. Oh, 61% of people know what they're doing. Okay, absolutely. Seawater freezes at -2 degrees Celsius. Has anyone ever been somewhere really cold where it's been icy? What do you put out on the ground? Salt. If you've ever been somewhere and they salt the roads, it's because of this reason. If you add salt, it's more difficult for those water molecules to get lined up into that nice hexagonal structure. And so it's more difficult for them to form ice. And so you lower the freezing point. So the more salt you have, the lower the freezing point. And so if you ever go out in Europe when it's been really icy, they scatter salt over the road. And that is meant to at least sort of melt away some of that ice. Okay. And so this little graph just shows you that. And it shows you a couple of things. So first of all, salinity is the x-axis here. So from low salinity, you can see PSU as equivalent to that per mil sign we had. And then increasing salinity off to 50 or so. And then temperature is up at the y-axis. And you can see that our blue line shows our freezing temperature. So at 0 PSU, at 0 salinity, our freezing temperature is 0 degrees Celsius. That's what we know that fresh water freezes at. But as we get saltier and saltier and saltier, that freezing point gets lower and lower. Okay? You can also see that there's a density on there, and we're not going to worry about that for now. Okay? So one last thing about the heat content of the oceans. So the heat content of the oceans is really important for stabilizing Earth's temperature. And water, we haven't had time to go into it, unfortunately, but water is this really amazing little molecule that does a number of things that it shouldn't do because of the way it's bonded both within the molecule and between those molecules. And one of its characteristics is that it takes a huge amount of energy to change its temperature. And you know that because when you're starving, you try and boil your water, and it takes forever to boil, right? If you're going to cook pasta or rice or something. And so it takes forever to boil because you need to put a lot of energy in. And the same way, you know that if you're doing the washing up, as I'm sure that you all do the washing up regularly, you put the hot water in and you can sort of wander off for 10 minutes and come back, and it will still be relatively warm. It takes a long time for that water to cool down. And the oceans are the same. And it has a really nice moderating effect. We know that here in Irvine because we know that we don't get as stupidly hot in the summer as some places inland do, like Riverside and sort of Vegas. So you can see that it has an effect. So on land, our sort of low temperature is of minus 88 degrees Celsius. Our ocean is minus 2 because we freeze at that point. On our high record, you can see that land also gets much hotter than our oceans do. So the range is much, much different. And those ocean temperatures really do affect our local climate and also things like affect the monsoon systems. So more about that in the atmosphere if you want to take that next quarter. But at a certain point, we get our water cold enough, and it takes quite a lot of effort to get it that cold. We get our water cold enough that it starts to freeze. And really little molecules line up and form these tiny little crystals that, remember, are less dense. They're less dense than water, okay? Because remember, they have that nice open hexagonal structure. And so what happens is when they form this ice, they're sort of mostly freshwater at this point, those little tiny crystals rise to the surface. And especially on calm water like this, they form that sort of grayish, sort of slushy-looking texture. It looks just like an oil slick on the surface. Okay? And that's something we call fragile ice. It's also known as grease ice because it looks like that oil slick. Okay? And if we continue that for a while, or if perhaps the ocean gets a little bit more rough, and we're able to develop some larger thicknesses, we get what we call pancake ice, which I love the idea of. And you can see little pieces of pancake ice floating around in that sort of fragile or that grease ice, that grayer stuff. So you can see here's a little circular piece of pancake ice. Okay. Why do you think those things look round? Why do you think they have these little raised edges? Anyone? Think about what might be happening on the water here. Why do you think they have these little raised ridges around the edge? Why do you think they continue to as they grow bigger? Okay, so here we have small pancake ice, medium pancake ice. Bet you can't guess what's coming next. Okay? But you can see even on this medium pancake ice, we have these raised edges. What's happening? What's causing that? Yeah?
Is it what you said about the ice pushing out the salt?
So it's a really good idea, but actually that happens deep down. Is this ice perfectly stationary? No. What might happen when the waves come past? Yeah, they just basically keep crashing into each other, and they do that in all directions, and so it makes them somewhat round, and it gives them this sort of ridge around the edge. Does that make sense? Or if you imagine all of those things sort of bumping into each other and sort of building up this edge to them. Okay? So yes, unsurprisingly, after small pancake ice and medium pancake ice, as it's sort of colder and more sort of developed, we get large pancake ice, okay? And eventually that large pancake ice sort of joins together and forms something that we call pack ice, okay? So these are sort of the chain of development of our sea ice. And you'll see these at different points in different parts of the Arctic at different times, okay? And so that thicker pack ice, once it's developed, it still will interact with itself and move. It's floating after all, and so it is still moving. And so it will form these sort of ridges and buckled edges. And we'll talk a little bit more about what we call those towards the end of today. Okay? And so you can see that, again, we're not talking about hundreds of meters of thickness here. We're talking about relatively thin layers of ice. Okay? So let's talk about brine. Brine is fun. You will realize this after I show you the video. So that salt that is in seawater that doesn't get accumulated in the ice structure tries to be excluded, okay? That gets left behind. But do you remember what happens to our freezing point as we get more and more salty water? What happens to that freezing point? it decreases. So if we keep increasing the concentration of salt left behind, especially in the little channels between the different pieces of ice, then we can get really high salinities, ridiculously high salinities, and that can prevent the remaining really salty water, which we call brine, in between the ice from freezing, okay? And so that brine is sort of trapped in little bubbles or channels as that ice builds up. And eventually it sort of joins together and sort of trickles down and seeps out at the bottom of the ice, okay? And so obviously the more time you give for that process to happen, for those brine sort of channels to form and join and sort of allow that brine a chance to travel out, then the fresher you get. And so that's something that if you're an Arctic explorer, next time you're hiking across the Arctic Ocean on the sea ice, then you look for older sea ice because it's likely to be much fresher. And after a few years, you could actually drink it, whereas just after 1 year, you couldn't drink the sea ice that's left. Okay? And so this little photo is it's a microscope image, really, that shows all of these different brine channels running through the ice as that brine comes down. And much more fun is to watch what happens when it comes out the bottom. So a few of you who've been in class with me before have seen my brinicle video, but it is a really fun video. So let's take a look.
When seawater freezes into sea ice, it releases its salt, creating super salty brine. This percolates through cracks in the ice into the seawater below. The brine then sinks because it's much denser than the surrounding water. It's also much colder, so the seawater freezes on contact, forming what's called a brinicle. Over the course of about 12 hours, the super salty ice stalactite grows, trapping anything it touches in ice. Most creatures here, like starfish, move far too slowly to escape these fingers of death.
So isn't that really cool? So my icy finger of death there. And it shows a couple of the things that we'll come back to, that the fact that this formation of sea ice and that the fact that this brine is excluded and then travels out at the bottom makes that seawater under the ice much, much more salty and so heavier and denser, and so it sinks. And do you remember I said that that's why sea ice is so important for things like the thermohaline circulation? Because we need this sea ice to form to make it salty enough that that cold, salty water is dense enough to sink right down into the deep ocean, okay? And so we'll talk again about those ideas on Wednesday. So sea ice is really fun, okay? So that's just to remind you of that. So how do we go about measuring sea ice? So this is something we'll talk a lot about on Wednesday, just sort of how we monitor sea ice using satellites now and how that's really helped us out. But we need to sort of come up with a couple of ways of describing it. Because unlike sort of land ice, where there's a solid block of it, sea ice can be a bit more patchy. And so it doesn't always form a constant layer. And usually it sort of occupies a percentage of the surface of the ocean. And so you can see two different images here showing different, what we would call concentrations of sea ice. The amount of sea ice occupies a different percentage here. And this can take a bit of practice doing, but if you look at the left-hand image, okay, what percentage of that field of view is ice cover rather than ocean cover? Okay, so what percentage of that field of view is ice cover rather than ocean? Any last estimates for me? Right. So most of us agree, 70% of us agree, that about 80% of the water there is covered by sea ice. What about that one? If you had to come up with a percentage for how much of the ocean there is covered by sea ice, what would you put? And I want you to think about it for a second. Write it down in your notes. Okay? And then compare it with the person next to you and behind you. Okay, does anyone have an estimate for me over here? What percentage did you say? 50 or so? Anyone else? No one brave enough to say anything different? 50 or so? You confident that if I gave you an image like this in an exam, you could give me a percentage? No, we'll get confident. I'm sure you can do this. Okay, so one trick that I was taught in a geology class, actually, when we have to count sort of different minerals, is instead of looking at the image as a whole, think about rearranging it in your head into all of the white stuff sort of organized on one side and all of the dark stuff on the other side, and see if that helps you work out whether it's maybe a quarter or a half or a 3/4. Okay? Maybe that might help. So my question for you is, when we say that sea ice extends, say, this far into the Atlantic or this far into the Pacific, what do we mean by that? Because you've just said that it can actually occupy different percentages. So at what point do we say, yes, there is sea ice, or no, there isn't? Sort of a gradual thing, right? So we actually set a cutoff. We say that if something is 30% sea ice or more, or if there's a concentration of 30% sea ice, then we count it as sea ice covered. Okay? And that's what things like our satellites will do. And if it's less than that, we don't count it as sea ice extent. Okay? So especially when we talk about maps of sea ice extent, when we talk about the changes that we're seeing on Wednesday and Friday, then that's what we mean. We mean a sea ice concentration of 30% or more counts as sea ice. Okay. So obviously, our sea ice forms in the winter usually when it gets cold enough for that water to freeze. And then, of course, we get spring and summer, and a certain amount of that ice will melt away because we have that energy coming in from the sun, warming the air, warming the ice itself. Even though it is reflective, it still absorbs some of that. And the key thing is that once you start melting your ice, you get these melt ponds developing. And now you don't have your nice reflective surface anymore. You have something that's really good at absorbing energy. So once you start having those melt ponds, it's relatively easy then to accelerate the melting of your sea ice. Especially as you get sort of deeper water, you can see the difference in the sort of darkness of the open water. You can see that really black stuff is that open water, and then the white sea ice, and then those sort of blue, those shallow melt ponds there. Okay? And we don't just melt it from above. Remember, the ocean still has an awful lot of heat in it. And just because we have this sort of cold air that's frozen the ice on the surface doesn't mean that there's still not heat coming from the ocean below. So we can also melt a certain amount of our sea ice from underneath. And it's worth remembering that. Okay? And so here's a sort of a comparison between what we call first-year ice. So first-year ice is ice that just formed that winter. Okay? So it's usually pretty thin, maybe sort of 30 centimeters or so, 12 inches or so. And it usually melts away again completely the following summer. So especially around the edges of the Arctic, this is what we tend to get. We tend to get this really temporary, relatively thin covering of sea ice that then will melt away again the following summer. But in some parts, some colder parts of the Arctic, we can develop multi-year sea ice. And we don't really get much older than, say, 10 or 11 years, okay? But we can get this multi-year sea ice, and this very cold-looking dude, again, is stood in a pit that has been dug into this multi-year sea ice. And this is much stronger, and there's much less brine in it, so we can sort of drink this if you melted it, okay? And that multi-year sea ice, as the name suggests, is stuck around for several years, and so it's had time to thicken and develop. And so this sort of brings us back to something that we need to get into our heads if we're going to think about some of the ways that we monitor sea ice. So I've shown you maps of the area of sea ice. But we're not just interested in sort of two dimensions. We're also interested in what depth of that sea ice there is as well. And that's especially important when we think about whether it's just that sort of single first-year sea ice or whether it's multi-year and thicker, okay? And so you can see here, it just shows that sea ice extent is something entirely different from sea ice volume. Volume also takes into account that depth. And we've been seeing changes in both, unsurprisingly, and we'll look more about that. And as you can see from the sort of sneak preview, in 1980, we had much greater ice volume. The ice that we had there tended to be much thicker, whereas today we're seeing much more of that first-year ice and that really thin ice. So it's already changing. Okay, so here is sort of coming back to those images I showed you right at the beginning. And my question for you is, I'm showing you here March and September for the Arctic, and September and February for the Antarctic. But why? If it's coldest in December, why do we see the maximum sea ice extent in March, when it's spring? And if it's warmest in July, why is the minimum sea ice extent defined in September? Why do you think? Yeah, absolutely. We're not thinking about just instantly how hot are we today. We're thinking cumulatively, absolutely. So just because it's hottest in August doesn't mean that it's not also going to be pretty warm in September, and so melt isn't going to continue, okay? So we start melting, say, from maybe March onwards as that temperature rises. And so we melt and melt and melt and melt until, say, the end of September, even if the maximum amount of melting is in those warmest months. And then at the end of September, we reach a point where it's cold enough again that we stop melting and start building up sea ice, okay? So the minimum point that we reach is at the end of the summer, when we've had all of those months of accumulated melting. And the same goes for the winter. Yes, it may be coldest in December, but it's still pretty damn cold up there in January as well. And so we're still going to continue accumulating snow, or not snow, sea ice, right until, say, March, when those temperatures finally start warming up again, okay? So it's a cumulative process, okay? So absolutely. Okay, so apart from just melting because of being exposed to warmer temperatures, but from both above and below, the other thing that we need to think about is the movement of sea ice. Because sea ice is not this sort of perfectly stationary ice cap that sits at the top of the planet. It's always moving around. It's sat on water that is moving and is exposed to wind that is also going to force it to move along, okay? And so just to remind you, there's so many cool videos of sea ice online. I do encourage you to go and watch. Look. Sea ice floats. There you can see it's bobbing up and down at the edge of the land here, okay? There it goes. Really fun, okay? And this is sort of one of the more dramatic videos I've found of it, and I can't work out whether it's time-lapse or not. I'm not entirely certain it is, but this is extremely fast movement of sea ice. I think someone in the comments called it a horizontal avalanche. And really, that's what it is. The power involved in these ocean currents, and also the wind as well, can really drive that sea ice quite fast, but not usually that fast. Okay? So sea ice moves, and you can see how, as it moves, it will crumple against each other. And so we sort of create areas where sort of crash zones, and also areas of more open water as well. Okay? So it can travel from sort of anything up to several kilometers a day. So some parts next to land may be sort of stuck around for a while, but especially in the open sort of parts of the Arctic Ocean, we can go pretty fast. And so it builds up certain features. So here's a really cool one. So as you saw, as that ice comes together, then that sort of thin layer can sort of fold over itself, and we call that rafting. And that happens especially in that first year sea ice as it's pushed together. And if you keep doing that, if you keep pushing that ice together, you can build up quite large thicknesses, sort of up to sort of tens of meters thickness of this sort of ice. And below, if anyone who sails, you recognize these words, below we have what's called a keel, and above we have what's called a sail. Okay, and the keel is usually much deeper than the sail, but obviously that sail will help force that ice along, given that it's much higher above the water. Okay, so we can get these sort of what we call compression ridges. There's a really cool sort of shot up there of a compression ridge on the sea ice. But if we're forcing ice together in some places, we're also probably moving it apart in others. And so we have also open areas of water, and this is pretty important. It's especially important if you're, say, a whale. So whales like to follow what we call these sort of linear stretches in the ice, these leads. Okay? And did anyone see, there was I think it was last year or the year before, a group of whales got stuck in Hudson Bay because it froze over completely, and they had to ice break sort of pockets for them to breathe so they could escape out to the ocean again. So these guys are sort of quite important for some of the wildlife. Okay? So we have these sort of linear stretches called leads, and that's sort of when we stretch the ice apart. We also just get sort of more open ocean sort of little circular areas, and we call those polynyas. At least I think that's how it's pronounced. Okay? You can see that often happens along the edges of land, where the ice is pulled away and it hasn't had time to form, but also further out as well. Okay? And those are important for exchanging gases and energy. So let's look at how water moves around the Arctic Ocean. So here you can see the main currents that flow around the Arctic. And you can see that, again, remember, our Arctic Ocean is a little ocean over the pole, and it's surrounded by land. And so you can see what we have there is something called a gyre, where the winds and the positions of the continents mean that water moves in a circular way. The fact that we have a big circular gyre in the Pacific is what creates our big Pacific garbage patch, the fact that all of those plastics are accumulating in the middle because that water just goes round and round. So we have that nice Beaufort gyre, and then we have this strong current called the transpolar drift that comes across from the coast of Russia and down past the coast of Greenland out to the Atlantic. But this area here is really where that ocean is sort of open between the Atlantic and the Arctic. Okay? And in comparison, you can see that we have warm water flowing up the coast of the UK and along sort of Norway up into the Arctic. Okay. This is what the currents would look like around Antarctica. Also what the winds look like in particular around Antarctica. And so you can see we're different again. Now we have a continent splodged over our pole, and around that we have ocean. And you can see that those little arrows there show the motion of the winds and the currents there as that ice would move. So my question for you is, which of these locations do you think we're more likely to have multi-year ice? Okay, so I'm going to give you a couple of minutes to think about it. Which of these locations would we be more likely to have multi-year ice, thinking about those currents? Okay. Last few votes? Okay, let's take a look and see what people think. You know what I'm going to do now, don't you? Talk to the people behind you and see if you can persuade them of your answer. Think about the geography, think about the winds and the currents. Okay, last few votes. Anyone else? Right, let's take a look and see if we've got any better with our answer. a lot better in terms of the spread, but I prefer the answer this way round. Okay, so I'll take this. So let's have a think about this. Okay, let's go back a second. Let's think about what ice would do in the Arctic Ocean. Okay? If my ice forms somewhere off North America, okay, what's it going to do? Is it going to head off into somewhere warmer and melt? What's it going to do, most likely? It's going to go round and round for a while, potentially, right? Okay? And so this is the idea, is that in the Arctic Ocean, that ice is much more trapped. So it's cold up there, and that ice is trapped. And we have these circular currents that go around. And so it's much more likely that that ice will get trapped close to the pole, where it's going to be cold even in the middle of summer. And so it's much more likely to last for more than 1 year. Whereas if we look at Antarctica, it may be really cold down there. But if you form as ice on the edge of Antarctica, we have these nice sort of currents and we have these nice winds that are going to force that ice to higher latitude, or so not to higher latitude, the lower latitudes, okay, sort of further towards the equator. And as it does that, it'll melt. And there's nothing keeping that ice close to Antarctica. It's free to escape out and melt. Does that make sense now? So in the Arctic, it's stuck, okay? And so it has to catch the right current to leave. Okay. So that's all for today.